Today I Anshu from BSc Chemistry on our first year. Today Inorganic Chemistry by Dr. S.P. Jauhar. Today I want to read chapter Chemistry of Noble Gases. The elements helium, neon, argon, krypton, xenon, radon compromises noble gases. The group of noble gases is regarded as zero group or group 18 of the periodic table. These are the gases at ordinary temperature and do not have chemical reactivity due to chemical inertness. These were called inert gases. However, nowadays a number of compounds of these gases, particularly of xenon, krypton, have been prepared. These show that these gases are not completely inert. Consequently, these gases are called noble gases instead of inert gases, which signifies that these gases have some reactivity because of low abundance of these gases on Earth. They have also been called rare gases. Occurrence of noble gases. The noble gases occur only as minor constituent in atmosphere due to inert nature of these gases. They always occur in free state. Except radon, all the gases are present in atmosphere in atomic state. The amount of noble gas present all these gases are present in atmosphere in atomic state. The amount of noble gas present in atmosphere in percent by volume is given by in table. Helium is also present in natural gas to extent of 2 to 7%. It is also present in small quantity in minerals of radioactive elements such as monazite, clavite, pitch blende, etc. Helium, neon, argon are found in water of certain spring. Radon is radioactive and does not occur in free state because it decays very rapidly. Helium was first discovered in sun atmosphere. It is now known that helium is being constantly produced in sun atmosphere by nuclear fusion reaction involving the formation of helium nucleus from 4 hydrogen atoms. History of discovery of noble gases. Noble gases are present mostly in the atmosphere. Their discovery is briefly discussed as follows. Discovery of argon. The main credit of the discovery of first noble gas argon goes to Cavendish in 1785. Henry Cavendish performed a number of experiments to determine the composition of air. He passed repeated electric sparks in a dry sample of air with an excess of oxygen to convert nitrogen of the air into nitrogen dioxide. According to the reaction, N2 plus 2O2 makes 2NO2. The gaseous mixture containing nitrogen dioxide and unreacted oxygen was absorbed in alkaline potassium sulfide solution. He observed that a small amount of residual gas, about 1 by 20th of the original volume of air, was left behind. He repeated the experiment again and again, and every time observed small trace of residual gas which was neither oxygen nor nitrogen. He could not understand the nature of these gases, residual gases which could not combine with oxygen. However, the observation of Cavendish remained unnoticed for a century. In 1894, Lord Rayleigh observed that the density of nitrogen isolated from the atmosphere is about 0.47% higher than the density of nitrogen prepared in laboratory. The thermal decomposition of ammonium nitrate. This minor discrepancy would have been ignored by many investigators. The Rayleigh, in collaboration with Ramsay, repeated the earlier experiment of Cavendish and concluded that the residual gas contained a new gas different from nitrogen. It was examined carefully by spectroscopy and was found to be unknown gas. The new gas was named argon. Discovery of helium. Helium was first detected spectroscopically by Lockyer in sun atmosphere in year 1868. While examining chromosphere of the sun during a total eclipse, as a result of their investigation, they conclude a new element called helium. Later on, Ramsay in 1895 also detected the gas on Earth from the radioactive minerals clavite camphor. In the same year, detected helium in trace in the atmosphere. Discovery of neon, krypton and argon. As Ramsay and Trevor performed certain experiment on argon, suspecting it to be a mixture of a number of similar constituent gases, they repeated experiment on liquefaction of air and its fractional distillation. The first fraction was found to be contain new element which give different spectrum. The element was called neon. And shortly afterward, they discovered two or more new elements of the further fractional distillation called krypton, meaning hidden, and xenon, meaning stranger. Discovery of radon. Radon was discovered by Dom in 1902 as a result of the study of distillation product of radium. Position of noble gases in periodic table. While building up periodic table, elements Mendeleev had not left any space for the noble gases. Obviously, he could not imagine the existence of elements which have almost no reactivity. Ramsay, the main discovery of these gases, proposed a new group for these elements on the basis of their atomic number and lack of chemical reactivity. This group is called zero group of the periodic table. The zero group also suggests chemical inertness or zero valency. Before the discovery of noble gases, they have sudden change from the most electronegative halogen to most electropositive alkali metal left hand side in the periodic table. The addition of zero group between 7th A group and 1st A group has solved this anomaly. The position of noble gases in periodic table was later on confirmed by Moseley, who constructed the periodic table on the basis of atomic number, and the value of atomic number of noble gases strongly suggests that they should be placed after halogen and before alkali metal. General characters of noble gases: electronic configuration. Except helium, the atoms of noble gas have 8 electrons in the valence shell, and the general electronic configuration of noble gas except helium may be expressed as ns2np6. Helium has the electronic configuration 1s2. These configuration being stable, the noble gases neither have any tendency to gain nor lose electron. Therefore, they do not enter into chemical combination. It is therefore reasonable to assume that the inert nature of noble gases is due to their stable electronic configuration. Helium, neon, argon, krypton and radon. Atomic number of helium 2, 10, neon 10, argon 18, krypton 36, krypton 54 and radon 86. Physical properties. Some of the important physical constant of noble gases are given in table. Existence. First physical property, existence. All the noble gases are monoatomic, colorless and odorless. The monoatomic state of these gases is due to stable electronic configuration of their atoms. As a result, they are not capable for combining even amongst themselves. The monoatomic nature of these gases is confirmed by their value of Cp by Cv, where Cp and Cv are the molar heat capacity at constant pressure and constant volume equal to 1.66. It is observed that for all monoatomic gases, Cp by Cv is close to 1.66 atomic radii. In the case of noble gases, the atomic radii correspond to van der Waals radii. As we go down the group, the van der Waals radius increases due to addition of new electron. Each shell ionization energy. The first ionization energy of noble gases are very high. This is attributed to the stable electronic configuration. However, the ionization energy decreases with increase in atomic number from helium to radon due to increasing atomic size. Electron affinity. Due to the stable ns2np6 electronic configuration, the noble gas atoms have no tendency to accept additional electron. Therefore, their electron affinity are nearly zero. Melting and boiling point. The melting and boiling point of noble gases are very low in comparison to those of other substances of comparable atomic and molecular masses. These indicate that there was no strong attractive force between the atoms which may hold the atoms together in liquid or in solid state. It has been established that one weak van der Waals force are present between the atoms of the noble gases in the liquid or the solid state. These van der Waals force increase with increase in atomic size of atom, and therefore the boiling point and melting point increases from helium to radon. As of liquefaction. 6th, the noble gases are not easily liquefied. This is due to fact that there are only weak van der Waals forces which hold atom together. This is also clear from the low value of heat of vaporization of these gases due to increase in atomic size and therefore increase in van der Waals forces. The assay of liquefaction increases down the group from helium to radon. Solubility in water. The noble gases are only slightly soluble in water. The solubility in general increase from helium to radon. The solubility of noble gases in water is due to dipole-induced dipole interaction. Water is polar molecule. When it comes from near a noble gas atom, it induces dipole in the noble gas atom by distorting or polarizing the symmetrical electron cloud of noble gas atom. As a result, an induced dipole appears on the noble gas atom, leading to interaction with the dipole of polar water molecule. Therefore, because of dipole-induced dipole interaction between water molecules and the noble gas atoms, the noble gas dissolves in water. As the size of noble gas atom increases, the extent of polarization also increases. Consequently, the magnitude of dipole-induced dipole interaction increases. Hence, the solubility of noble gases in water increases from helium to radon. 8. General chemical characters. In general, noble gases are not very reactive, and their inertness to chemical reactivity is attributed to the following reason. The noble gases have complete filled ns2np6 electronic configuration in their valence shell. Second, the noble gases have very high ionization energy. The electron affinity of noble gases are almost zero. Therefore, they have neither tendency to gain nor to lose any electron and do not enter into chemical combination. However, in recent years, it has been found that noble gas, particularly xenon krypton, form some compound. Chemistry of compounds of noble gases. Prior to 1962, it was believed that the noble gases do not combine at all and no compound of noble gases were formed, though from time to time some attempts have been made to test the reactivity of noble gases, yet the gases were thought to be inert. This was also supported by the following reason. The atom has stable complete filled electronic shell. They have high ionization energy. The noble gases have almost zero electron affinity. Therefore, they do not have any tendency to gain or lose or share an electron with the other atom. The above reason discouraged the chemists to make serious attempts to prepare compound of noble gases. In 1962, and Bartlett, while investigating the chemistry of PTF6, noticed that platinum hexafluoride acts as a powerful oxidizing agent which combines with molecular oxygen to form ionic compound dioxygene hexafluoroplatinate. This indicates that PTF6 has oxidized O2 to O2 positive. Now oxygen and xenon have some similarity, and this led Bartlett to try reaction between xenon and PTF6 in a similar manner. For example, the first ionization energy of xenon gas is comparable to that of oxygen. For the process, O2 make O2 positive plus me electron. Second, the molecular diameter of oxygen and atomic radius of xenon are almost same. With this assumption, Bartlett treats xenon and platinum hexafluoride in gaseous phase. An orange-yellow solid xenon hexafluoroplatinate of the composition XZPTF6 was obtained. On analysis, this compound was found to be ionic compound, and this marked the first compound of any noble gas. The formation of the ionic compound has demonstrated the xenon is not totally inert, and it is not possible to remove an electron from xenon atom. This discovery attracted many scientists for XZF2 and have been prepared in laboratory. Thus, noble gas chemistry begins. Among these noble gases, xenon form a large number of compounds with fluorine or with oxygen, and krypton form only few compounds. Some important stable compounds of xenon in different oxidation states are listed in table 3. Before discussing the chemistry of compounds of noble gas, it becomes important to understand the answer to some important questions. What are the factors responsible for late discovery of compound of noble gases? Why do most of the compounds involve xenon, fluorine and oxygen? Late discovery of compound of noble gases. Prior to 1962, it was believed that the noble gases do not combine because they have stable electronic configuration. Many attempts were made to prepare their compound, but all these attempts proved to be unsuccessful. Moisen in 1895 have reported that there was no chemical reactivity between fluorine and argon. This led Ramsay to conclude that the noble gases are chemically inert. This conclusion was also supported by the concept of valency. According to this, shell has been taken as the criterion of stability and inertness. That is why the noble gases were assigned zero valency, and this group were designated as zero group. However, the concept of octet suffered setback because of the discovery of compounds like PF6, SF6 and IF7, which had made more than 8 electrons in their valence shell. This, however, did not make the scientists to make more serious attempts because the noble gases seemed to have neither any tendency to lose electron nor any tendency to gain electron. Some other factors in addition to chemical inertness of noble gases which leads to the late discovery of noble gases compounds are lack of availability of fluorine of good quality, non-availability of fluorine-resistant grease, non-availability of inert material to handle fluorine gas, non-availability of large quantities of noble gases. Why do most of the compounds involve xenon, fluorine and oxygen? When we know that the tendency of an atom to lose electron is given by ionization energy. If we carefully, the ionization energy of these elements have been given in table 1. It is noticed that leaving aside radon, which is unstable, only xenon to some extent krypton and has ionization energy comparable with elements like carbon, nitrogen and oxygen. Largest number of compound krypton come next, neon, argon and helium, which have much krypton is due to their tendency to lose electron. It suggested that the combining atom should have strong affinity for electron, that is, should be strongly electronegative. Now in periodic table, fluorine and oxygen have high electron affinity and therefore have strong tendency to accept electrons. Xenon combined directly with fluorine, its compound with oxygen are obtained from its fluoride. Xenon chloride is non, but it is not stable. Only one compound with nitrogen is non, but it is highly unstable. Compound of xenon. Xenon form a large variety of compound with fluorine and oxygen in different oxidation state. These are xenon fluoride, xenon oxide and xenon oxyfluoride. Xenon second compound, xenon plus 2 oxidation state compound, xenon difluoride. It can be prepared by the following method. Xenon difluoride is the best prepared by heating mixture of xenon and fluorine in molecular ratio of 2:1 at 40 degrees Celsius in a sealed nickel tube. On cooling quickly, a colorless solid XeF2 is obtained. Excess of xenon is used to avoid the formation of any higher fluoride such as XeF4. It can also be prepared by subjecting a mixture of xenon fluorine in molar ratio of 2:1 to electric discharge. Xe plus MEF to make electric discharge makes XeF2. It is also formed by photochemical combination of xenon fluorine in the presence of mercury vapor. Xe plus F2 make Hg vapors XeF2. It can also be prepared quantitatively by fluorination of xenon by oxidation by monofluoride O2F2 at minus 78 degrees Celsius. Xe plus O2F2 in minus 78 degrees Celsius prepares XeF2. Properties. Xenon difluoride is a colorless crystalline solid which melts at 129 degrees Celsius. It is least volatile. Xenon fluoride, it is stable in pure state, dry state, and can be stored in nickel container. It is dissolved in hydrogen fluoride without reacting with it. It reacts with hydrogen to give hydrogen fluoride and xenons. It hydrolyzes slowly but completely in acidic and neutral or alkaline solution. It oxidizes iodine in the presence of BF3 to give IF. It reacts with NO and NO2. It reacts with sulfur trioxide to give xenon. It is mild fluorinating agent, thus it reacts with benzene to give fluorobenzene. It is also fluorinates ethylene to 1,1-difluoroethane. It is also a strongly oxidizing agent. It oxidizes HCl to Cl2, C3 to C4, chromium 3 to chromium 4. Xenon difluoride is an anhydrous hydrogen fluoride. Reacts readily with platinum, metal, sulfur powder and iridium to produce highest fluoride. In BrF2 solution, xenon difluoride acts as a Lewis base and form adducts with composition XeF2 MF5, XeF2.2F2 MF5 and 2 XeF2 MF5. These compounds XeF2 and SbF5 and XeF2.AsF5 exist as ionic species as XeF5 plus SbF6 and XeF plus AsF6 negative respectively similar. The compound XeF2.2SbF5 has been shown to contain XeF plus and Sb2F11. The XeF positive ions is strongly bonded to Sb2F11 by a fluoride bridge between Xe and Sb. The ions contains two octahedral linked by shared F as shown ahead. XeF2 also reacts with arsenic pentafluoride in different stoichiometry. The ionic Xe2F3 positive has been expected linear geometry around xenon and angular geometry around the xenon fluoride. Structure and shape of XeF2 molecule. Spectroscopy analysis has been shown that XeF2 molecules has linear geometry. This is explained on the basis of the valence bond theory as follows. Xenon is ground state, has valence shell electronic configuration is 5s2 5p6 as shown in figure. One of the 5p electron get unpaired and promoted to 5d orbital resulting in two unpaired electron, one in 5p and one in 5d. In the excited state of xenon, 5 orbitals hybridize to give sp3d hybrid orbital which adopt trigonal bipyramidal geometry. The two orbitals containing single electron overlap with two fluorine atom forming 2 XeF bond. The xenon and two fluorine atoms lies in a straight line. Equatorial position are occupied by 3 lone pair of the electrons and the molecule has such linear geometry as shown in a figure. As in XeF4 compound Preparation, it can be prepared by the following method. It is prepared by good yield of heating mixture of xenon and fluoride in the molar ratio 1:5 in a nickel vessel at 400 degrees Celsius under a pressure of 5 to 6 atmosphere. It is also synthesized by passing an electric discharge through a mixture of xenon and fluoride in molar ratio 1:2 at minus 78 degrees Celsius. The pressure is of between 2 to 15 mm of Hg. Properties. The important property of XeF4 are: it is colorless crystalline solid. Its melting point is 117.1 degrees Celsius. It sublimates easily. It dissolves in iodine pentafluoride and hydrogen fluoride without reacting. It is oxidized by hydrogen 2HF at 30 degrees Celsius. It is stronger fluorinating agent than XeF2. It converts Hg to HgF2, platinum to PtF4, and NO to NO2 to NOF, and NO2F, SbF4, RSF6, etc. It reacts with boron trichloride to form boron trifluoride. It undergoes dispersion in water, giving highly explosive solid compounds. But if the reaction is controlled at minus 80 degrees Celsius, form xenon oxyfluoride. It combines with molten TAF5 to form straw-colored XeTAF6 twice. It forms addition compound with antimony pentafluoride. XeF3 has T-shaped structure with two positions occupied by a lone pair as shown below. The electronic structure of XeF4 may be written as: spectroscopy method has been shown by XeF4 has square planar structure. This can be explained on the basis of valence bond theory. Xenon atom in the ground state has 5s to 5p6 outer shell electronic configuration. In the formation of XeF4 molecule, 2 of the p orbital electrons are promoted to 5d orbital, so that there are 4 unpaired electrons, and the 6 orbitals get hybridized to form 6sp3d2 hybrid orbital, and these 6sp3d2 hybrid orbitals adopt octahedral geometry. 4 of these containing single electron overlap with 2p orbital of fluorine to form 4 xenon fluoride bond. The remaining 2 positions are occupied by a lone pair. Thus, as shown in figure 3, the molecule has square planar shape. Formation of XeF4 molecule.